Covalent bonds. In this video we will be looking at the particle model, introduction to covalent bonding, single and double bond, covalent structures, graphite and graphene, fullerenes. The particle model. The particle model is a basic idea in chemistry that helps explain how matter behaves. It shows that everything is made up of tiny particles, which could be atoms, molecules, or ions. These particles are what make up solids, liquids, and gases, and they behave differently in each state. Now let's see this with the help of an example. Consider water. In the solid state, ice, the particles are packed closely together and only vibrate in place. When ice is heated and melts into a liquid, the particles move more freely, but they are still close together. If the liquid water is heated further and turns into steam, gas, the particles move much faster and are spread out. This explains how heating changes the movement and arrangement of particles, and how the states of matter change from solid to liquid to gas. Introduction to covalent bonding. Covalent bonding is a fundamental type of chemical bonding that occurs when two atoms share one or more pairs of electrons. This sharing allows each atom to achieve a stable electronic configuration, typically resembling that of noble gases. Atoms bond with each other by either sharing or transferring electrons. A covalent bond forms when two atoms share a pair of electrons. The number of electrons shared depends on how many are needed for an atom to fill its outer shell. This type of chemical bond typically occurs between nonmetal elements, or in compounds composed of nonmetals. Single and double bond. A single bond occurs when two atoms share one pair of valence electrons. Examples of single bonds include hydrogen chloride, HCl, and water, H2O. A double bond forms when two atoms share two pairs of electrons, a total of 4 bonding electrons. Examples of double bonds include carbon dioxide, CO2, and ethylene, C2H4. Covalent structures. When atoms bond covalently, they form different structures depending on the number of atoms and the type of bond. Most covalent structures do not conduct electricity, because they lack free-moving delocalized electrons, or ions to carry charge. Delocalized electrons are electrons that are not associated with a single atom or covalent bond in an atom, ion, or molecule. There are 3 primary types of covalent structures. Giant covalent structure. A giant covalent structure is a 3-dimensional network of atoms joined by covalent bonds. Unlike other covalent substances, a few form giant structures instead of small molecules. In giant molecular structures, billions of atoms are bonded together by strong covalent bonds. Diamond is a giant covalent structure where each carbon atom forms covalent bonds with 4 other carbon atoms in a tetrahedral, 3-dimensional arrangement. Giant covalent structures have high melting points due to the presence of strong covalent bonds between the atoms. They are mostly solids at room temperature and require a lot of energy to break the bonds between the atoms. Small molecules. Each molecule contains only a few atoms with strong covalent bonds. Different molecules are held together by weak intermolecular forces. Water is made of small molecules. A water molecule, H2O, has 2 hydrogen atoms and 1 oxygen atom. Small molecules have weak intermolecular forces, resulting in low melting and boiling points due to the low amount of energy needed for transition. The small molecules are typically gaseous or liquid at room temperature. Large molecules. The atoms in a large molecule are connected by strong covalent bonds forming chains of variable length. The intermolecular forces are stronger in large molecules. Polyethene molecules contain thousands of carbon atoms joined together in a chain. The strong intermolecular forces in large molecules result in higher melting, and boiling points compared to small molecules. Large molecules are mostly solids at room temperature. Summary: giant molecules have large, interconnected networks of atoms with strong covalent bonds, making them very strong and stable. For example, diamond, graphite. Small molecules consist of a few atoms bonded covalently and have distinct, individual molecules. For example, water, carbon dioxide. Large molecules, macromolecules, are long chains or networks of smaller units and can be natural proteins, DNA, or synthetic plastics. Graphite and graphene. Graphite is a form of carbon with a unique crystalline structure, expressed by the chemical symbol C. It is a type of giant covalent structure. However, it differs from other giant covalent substances. In graphite, each carbon atom forms hexagonal rings by bonding to 3 others in layers. Each carbon atom possesses one spare electron, which is delocalized and free to move throughout the structure, allowing for the flow of electric current. Graphite is much softer than diamond, because its layers can slide over each other, as they are not covalently bonded. Graphene is an allotrope of carbon. It is a single layer of graphite, with strong covalent bonds that allow it to conduct electricity. It is used in high-tech electronics and composites. Fullerenes. Fullerenes are carbon molecules with hollow shapes. They consist of hexagonal rings of carbon atoms joined by covalent bonds. They can be arranged as a sphere or a tube called a nanotube. The Buckminster fullerene is the very first fullerene to have been discovered, and it is made up of 60 carbon atoms. Buckminster fullerene has a low melting point, as the weak intermolecular forces between the molecules of Buckminster fullerene require less energy to overcome. A nanotube is a cylindrical shaped structure made from a single layer of graphene. It conducts electricity through delocalized electrons. It consists of carbon atoms that are arranged in cylindrical tubes. They possess remarkable tensile strength, and they are incredibly resistant to breakage when subjected to pulling forces. Fullerenes have various applications, such as drug delivery, high-tech electronics, and lubrication. They are widely used in these fields due to their unique properties.